This is the video for the heat and mass homework number 7. In the first problem here, we were looking to find the temperature of the wire given in the problem with external force or external convection basically which was going on for this problem statement. So we were given these values, and we were given a current and a resistance. And then so what we had to do was find our Reynolds number, like almost in every problem. We define our Reynolds number and then use that to help find our Nusselt number. And these values were able to kick out because we needed our Nusselt number to find our heat transfer coefficient. So once you get your heat transfer coefficient, you can save this for a little bit later, but you come back and you have to use your resistance and your current to find a Q, and then you find your Q and you plug it into your convection equation, and you're able to find the temperature of your wire. In the second problem, we were once again looking for the heat transfer coefficient of the cooling water though, and the velocity of the cooling water. So we used our given values, and this time we were able to find the Q per each tube as we did the total over each tube, and then we were able to find our temperature for the log mean, and then we once again manipulate this equation to find our heat transfer coefficient, which is here, which is of the water which we're looking for. Then we find our m dot, which in turn, after we get our m dot, we can use the V average equation, which is 4m dot over rho pi d squared, get our velocity, which is what they asked for. In the third question, we were looking for another temperature, but this time it was the temperature of light. So we had 5% and 95% given to heat, just a bunch of different values. And so we had to go look up our properties table, use our Rayleigh number this time instead of a Reynolds number to find our Nusselt number. And then we use that Nusselt number once again to find our heat transfer coefficient. And then once we do that, we have to do the total because we had convection and radiation. So we do convection plus radiation, and then we find the temperature of the convection, which was 175. But the trick with this problem was we had to guess 170 to get our properties. And because 175 was close enough to 170, we don't have to repeat the problem with a new temperature. And then the final problem was looking for another rate. So, and we were looking for which is higher, basically between a sphere and a flat plate. So we go through our whole problem, and we have to do this basically the whole thing twice. Solve for our L star, which is this equation, which kicks out this value, which we're able to use a CR value, critical R value, which then we plug in to find a heat flux, and then we use that to find our rate value. This is for the sphere, and then we repeat the whole process again for the flat plate, basically not changing anything except this little L here for the differences in geometry. Then we kick out these values of the heat flux and our rate law, or our rate. And we're able to find that the flat plate, or the square heater, basically is the same idea of geometry, has a higher rate of vaporization for its geometry. There were no real points of confusion in this section of homework. It was just still a lot of information and still trying to determine which Nusselt number, how to read the problem correctly, and determine which equations, which route to take in order to solve the problem correctly.